questions 21 through 25 on the 2021 Grade 8 Gauss Math Contest. One evaluated the sum of the digits of the integer equal to 10 to the power of 2021 minus 2021 is. Well, 10 to the power of 2021 is a big number, so let's just try to get some sort of a pattern here. Let's say it was just 10 to the power of 4. Let's see what we get. Well, 10 to the power of 4 is simply 1 followed by 4 zeros. 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4. And that's going to be subtracting from it 2021. When you do that, you get 7979. Okay, so far so good. Now let's try 10 to the power of 5, see what happens. This is now one more 0. So 0, 0, 0, 0, 0. And then again, let's do that subtraction. And when I do, now I get 9. And then 7979. Okay, great. So let's do this once more, see what kind of a pattern we have. If I do 10 to the power of 6, I get 1, 0, 0, 0, 0, 0, 0. Minus 2021 would give me 997979. So as you can see, you're just going to increase by a 9 each time. When it was 10 to the power of 4, it was just this. When it was 10 to the power of 5, it was 1 9 with that. When it was 10 to the power of 6, it was 2 9s, and then that 7979. So it seems to me that this number and this number of 9s is connected. And the relation is basically that the number of 9s that shows up is this number minus 4. So in this case, it was 4 minus 4, so 0 9 showed up here. Here was 5 minus 4, that's why we had 1 9. And here it's 6 minus 4, that's why we had 2 9s. So when you have 10 to the power of 2021 minus 2021, obviously this is going to be some big long number, minus 2021. That's going to be 7979, but then how many 9s will go here? 9, 9, how many 9s? Well, we just figured it out. It's this number minus 4. So it would be 2021 minus 4, which is 2017. So 2017 9s would be here. So now we have to find the sum of the digits. Okay, the sum of the digits of this. That's not a problem. There's 2017 9s, so they contribute to the sum 2017 times. And then we add the 7, then we add the 9, then we add the 7, and then we add the 9. So this is 18153, and then this part here is 32. And then when you add it all up, it's 18185. Number 21, the answer is E. The prime numbers 23 and 29 are consecutive prime numbers since 23 is the smallest prime number that is greater than the prime number 23. 29 is the smallest prime number that is greater than the prime number 23. How many positive integers less than 900 can be written as the product of 2 or more consecutive prime numbers? First, let's write down some of the first few prime numbers. We get an understanding of what we're working with here. So 2, 3, 5, 7, 11, 17, 19, 23, 29, and I'll put one more, 31. So first, let's start off with just 2 consecutive prime numbers. Then we'll go to 3, and then we'll go to 4. So 2 consecutive prime numbers. Okay, well, let's see here. How about I want to see what I have to do to ensure that I'm less than 900. 29 and 31, if I selected those and I multiplied them because they want the product, right? So 29 times 31, what is that? That is 899. So that just makes it. So I'm pretty sure that's the end of the road for 2. So I can use any 2 consecutive as long as I don't go beyond that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So those 10 consecutive. So I'll just put that in there, 10 to represent that. That's how many I get with 2. How about if I want 3 consecutive prime numbers? Can I get a product less than 900? Well, let's see. If I chose the first 3, 2 times 3 times 5, that is 30. Okay, that works. How about the next 3? 3 times 5 times 7, that's 245. That works. The next one, 5 times 7 times 11, that's 385. That works. The next one, 7 times 11 times 13, that's 1001. Oh, that does not work because that exceeds 900. So I got another 3. Okay, now let's try 4 consecutive prime numbers. I think here we'll run out pretty quickly. The first one, 2 times 3 times 5 times 7, that is 210. Okay, that works. And let's try the next one, 3 times 5 times 7 times 11, and that is 1155, so that doesn't work. So here I pick up just one more. So I got these 10, these 3, and this 1. That's 14 in total. And therefore, number 22, the answer is A. A dog's leash is 4 meters long and is attached to the corner of a 2x2 square doghouse at C, as shown. The dog is attached to the other end of the leash at D. What is the area outside of the doghouse in which the dog can play? Well, we have to sort of figure out what are the boundaries here. So here's the 2x2. And then we've got this leash here. Now the leash is 4 in terms of its length. So it's going to be able to go up until there. So, and it's going to be able to go all the way up until here. So it'll be able to essentially go all the way like a circle. So all the way around. So basically like that. So that's basically the boundary of the region that the dog can travel. But once the rope comes here, this part of the rope cannot move anymore. But this part of the rope can. It can continue to kind of go up like this. Just this part. And similarly, that part of the rope can also go like that. So we can create these quarter circles. And that will be the full region. So the first part is this big quarter circle right here. And that big quarter circle, or 3/4 of a circle I should say, is 3/4 pi r squared, where r is equal to 4, right? Because from here to here is 4. And then what we have to do is add to it these 2 small quarter circles. So we are adding 2 quarter circles, so pi r squared divided by 4, like that. Where small r is 2 this time, because from here to here is 2. Okay, so let's plug this in. 3/4 pi times 16, and then pi over, this is going to be just pi times 4 over 2. So this becomes 16 divided by 4 is 4. 4 times 3 is 12. So 12 pi plus 2 pi, and that is just 14 pi. So there we go, 14 pi, number 23. The answer is A. Jonas builds a large n by n by n cube using 1 by 1 by 1 cubes, each having the net shown. What is the smallest value of n for which the sum of the exterior faces of the n by n cube can be greater than 1500? So here is a cube, and what we want to do is talk about the types of the faces. There's really only 3 types. There's the faces that are sort of in the middle like that, inside this small circle. And then we have the ones that cover 2, like that. And then we have the corner ones the corner ones would actually contribute 3 faces, like that. Okay, so let's talk about each. First, let's talk about the ones that are in the middle. This is 1 and this is 1. So if the full distance from here to here is n, the distance from here to here is really n minus 2. So that square is really an n minus 2 by an n minus 2 square. And there's 6 faces, right, of the cube. So that has to be multiplied by 6. And I want the smallest value of n for which the sum of the exterior faces is greater than 1500. So that is achieved by maximizing the numbers that appear on these external faces. So these ones only involve one face, so I want the maximum. The maximum here is this 2. So I'm going to multiply all those by 2. That's going to be what it contributes to the sum. Okay, so far so good. Now let's talk about the corners, these guys right here. As you can see, on each face, there's going to be 4 quarters. So that's just a standard. And since there's 6 faces, there's 6 times 4 quarters. So that's 24. Now, those 24, as you can clearly see from here, each of them has 3 faces that contribute to the sum on the exterior. So I'll split that up into 8 faces, 8 faces, 8 faces. And each of those I have to choose a number from here. But it's not that simple because I can't just choose any of these. I have to choose 3 such that they share a corner. Do you see how they share a corner there? For example, 1 and 2 do not share a corner. No matter how you look at it, it will not share a corner. If you draw a very rough diagram of this cube, you'll understand what I mean. Let's just make a little diagram here. So let's put in the numbers. Let's put in the numbers that are here on this cube. So I put the 1 on top, the 2 goes on the bottom, the 0s go on the sides, and in the front would be the -1, and on the very back would be the -2. Squeeze that in there somewhere, -2. So as you can see, the only way you can choose 3 is if they share a corner. This corner right here, for example. And we want to do it in a way so that the numbers are maximum. And the only way to do that is with 2, 0, 1. So 2, 0, and -1. That's what I meant to say. So as you can see, this 2, which is on the bottom, this 0, which is on the side, and this -1, which is on the front face, they share a corner. And that's the only way that we can put the numbers here. It would be like this, 2, 0, and -1 to maximize the sum. We would like to use the 1, but unfortunately we can't. So that means the 8 contributes, you multiply that by a 2. The next 8, we multiply that by 0, and the next 8, we multiply that by -1. So this contributes to 16, this contributes to 0, and this contributes to -8. Now we start to talk about these guys. These are the ones on the sides. So this was in the middle, right? These were the corners, and now we talk about the sides. The sides are not that complicated. Remember, this was n from there to there. This, therefore, is n minus 2. So n minus 2 are how many sides appear in this little block right there. But remember, there's 4 blocks. There's one here, there's one here, there's one here, and one there. So 4 blocks. You multiply by 4. And then there's 6 faces, so you got to multiply by 6. And then now we got to figure out how do we assign the numbers, correct? So this is basically 24 times n minus 2. So first I'm going to break it up into 12 times n minus 2, and then the other 12 times n minus 2. And for each, we have to assign 2 numbers, one number here and one number there, in a way to maximize the sum. And after you fiddle around with this and this, you realize that the way to maximize the sum, interestingly, is to choose 2 and 0. Because remember, we can't choose any 2 numbers. They have to share a side. And for example, 2 and 2 and 0 share a side, right? So that's why we choose 2 and 0. So when we do, this becomes 24n minus 2, and this becomes just 0. Okay, so now we add it all up. We have to add up all of these guys. This one, this one, this one, and this one. Okay, so let's do that. So we have, let's see here, 12 times n minus 2 squared plus 16 minus 8, well, that's just 8, plus 24n minus 48. Correct? And all of that has to be greater than 1500. We have to figure out the smallest n that satisfies that. Okay, so let's expand this. This is going to be 12n squared. And then that's going to be 4n, so minus 4n, so that's going to be minus 48n. Plus 4, so plus 48. Plus 8 plus 24n minus 48, and that's all greater than 1500. So let's move this up now. So when we collect like terms, we got 12n squared, and then we have minus 24n plus 8 is greater than 1500. Divide through by 4. 3n squared minus 6n plus 2, 375. Put everything on one side. 3n squared minus 6n minus 373 greater than 0. Now we have to use a quadratic. So n would be 6 plus or minus minus 6 squared minus 4 times 3 times negative 373. All over 2 times 3. And when you crunch out those numbers, you get 12.19. Now, as one of the values. Now, when you put n equals 12, because n obviously has to be an integer, right? N represents the sides of a cube. When you put n equals 12, you will get a value that is less than 0. So the only time this equation becomes greater than 0 is when n equals 13. And you can plug that in to verify. So n equals 13 is the smallest value that makes this whole equation work. And therefore, number 24, the answer is D. Square PQRS has side length of 8. It is split into 4 rectangular regions by 2 line segments, one parallel to PQ and one parallel to QR. There are n ways in which these line segments can be drawn so that the area of the 4 rectangular regions is a positive integer. What is the remainder when n squared is divided by 100? Well, let's talk about it. First, we have just our standard PQRS. And here we go, PQRS. And this is split up into segments of length 8, right? So each side is 8. So I'm just going to break it up into integers. So this is 1, 2, 3, 4, 5, 6, 7, and then this would be 8 right at the very end. And in a very similar way, we do the same thing on the side, and it would basically be identical. 1, 2, 3, 4, 5, 6, 7, 8, like that. Now, let's break it up into different categories. The first category is when the breaks are made such that they're made on an integer. So, for example, let's say I made the first one to happen entirely that it cuts through 2. And the second one, anywhere really, let's say it cuts through 5. So those are my two splits. And let's see what happens. So the first one, the area would be 2 times 5, which is 10. The next one, the area would be 6 times 5, which is 30. 2 times 3, which is 6. And 6 times 3, which is 18, right? So clearly, those are all positive integers, so that's great. And now we have to figure out how many ways are there to do this. The one that goes top to bottom, obviously, that's the vertical, so I'll just call that the V. And the one that goes left to right, that's obviously horizontal, so I'll just call that H. V for vertical, H for horizontal, right? Whatever you want to call them. For V, there's 7 possible choices. Either 1, 2, 3, 4, 5, 6, 7, right? Can't be 8 because then it wouldn't be cut into 4 different segments. If you made the line right on QR, it would basically end up cutting it into 2 segments. So we have 7 choices for V when we want just integers. And very similarly, there's 7 choices for H. So 7 times 7 is 49. So there you go. That's part of the answer. But we've got a few more scenarios, right? The next scenario is when you have the following. We made the first cuts with integers, but what if you made a cut so that it is halfway, like 0.5, so 1.5. I'm making that cut at 1.5. So that is going to give me another scenario. So I'll call this one integers, where both V and H were made where there's an integer. The next one I'm going to call 0.5. In particular, 0.5 for my horizontal cut for the H, right? So for example, 1.5 was what I drew on the diagram. Now what happens? How do we get integers? If H is a 0.5, 1.5, 2.5, like that, the only time you're going to get integer values if V is equal to either 2, 4, or 6. And I'll prove it to you with one example. Let's say V is 2, right? Okay, if V is 2, then what do we have for our areas? Let's write them in. The first one would be 2 times 1.5, which is 3. The next area would be 2 times 8 minus 1.5, which is 6.5. So 6.5 times 2 is 13. And the next one on this side here, that would be what, 6, right? So 6 times 1.5 is 9. And then on this side, it would be 6.5 times 6, which is 39. So great, it all works out. So as I hope I've proved, it works for the 0.5s only when V is either 2, 4, or 6. So that means if I were to figure out how many total, for V it looks like I've got 3 choices, either 2, 4, or 6. And for H, how many 0.5s? Okay, that's gonna gotta think about this. I get 0.5, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5, 7.5. So 1, 2, 3, 4, 5, 6, 7, 8. 8 of those. So 8 times 8 possible choices for the H. And you got to multiply them, so that's 24. Okay, so hopefully that makes sense. Now let's continue with that. The next one, continuing in the same way, is what happens now. I did 0.5, right? So what happens if I were to try to multiply by a 3? Well, how about if I had like a 0.33, which is really just 0.3 repeat. The 0.3s for the H. I would have to multiply by 3 in order to make that an integer, correct? But the problem is it will for the first one, but it falls apart for the next one. So let me just give you a quick example. Let's say I chose my H to be 1.33, right? And then therefore I chose my V to be the number 3. So the 1.33 cut is somewhere here, right? And then the 3 cut is right here. Let's see what happens. For the first area, I'll just draw it really quickly over here on the side. This is 3 and this is your 1.3 repeat. This becomes 4. So you think, okay, that's great. That works out. But unfortunately, it falls apart immediately on the next one. The next one would be 5 times 1.33, and that is unfortunately 6.66, which is not an integer. So for these 0.3s, it doesn't work. Okay, so now let's go back and look at what else we can do. The next one is if we have a situation where you're multiplying by 4 this time. We tried the 1, right? That was no problem. 2, we got some solutions. 3, we got nothing. How about 4? In order to get an integer, that would now mean a 0.25. Those guys for h. And after careful thought, you will see that this only works. It only works with one value for v. That's when v is 4. So I'll give an example. Let's say h is 1.25. Okay, so we'll do it. We can do it on this diagram, not a problem. So approximately here, right? 1.25. And we're using v equals 4. So right down the middle. Okay, let's see what numbers we get. So we've got 1.25 and we've got 4. So the first one, 4 times 1.25, well, obviously that's going to be 5. So that's great. So there's a 5 in here. And then this is going to be 5 also. And then what about the next one? The next one would be 8 minus 1.25, which is 6.75 times 4, which is 27. And this also is 27. So it all works out. So how many for v and h? Well, for v, there's only one number, that being the 4. For h, though, so I got to think about this. How many 0.25s? Well, from 0 to 1, there's 0.25, there's 0.5, and 0.75, right? 0.25, 0.5, and 0.75. But I don't want to include this guy because this guy's already been included up here. So I just want to include these guys. So there's really only 2 between each integer. So 2 there, and so on. So 2, 4, 6, 8, 10, 12, 14, 16. 16 of those that would fit for h. So 1 times 16 is just 16. Okay. And then we just keep going. But for the sake of time, I will just write these out. If you try the next one, right, which is 5, where we had done v equals 3 and then 4, 3 and 4. If you do 5, then we have to use 0.2s, correct, for the h, if v equals 5. And I will let you figure out why, but there's no solutions here. It does not work. Meaning you won't be able to get a scenario where all 4 are integers. And in a very similar way, if you keep going, if v equals 6, then you would get this 0.16 repeat, right? 1 over 6 basically for the h. And very similarly, again, it does not work. And then the last one, when v equals 6, you get a 1 over 7 scenario, 1 over 7s, and for h. And very similarly, it doesn't work. It doesn't create a scenario where you have 4 separate areas that are all integers. So let's recap here. The only ones I got to work were these 49, these 24, and these 16. Correct? But here's the thing. These ones are perfectly fine the way they are. No problem. But these ones, we can double them because notice that scenario can also be flipped. We can also have h and v flipped. So you can have the 3 possible numbers for h and 8 possible numbers for v. And that would give you another 24. So you notice here I gave you v equals 2 and h equals 1.5. I could have also done the same thing as v equals 1.5 and h equals 2. So that's why you get another 24. And very similarly down here, you can do the exact same thing. You notice how I gave an example of v equals 4 and h equals 1.25. I can also flip it by giving, for example, v equals 1.25 and h equals 4. And that would give me an additional 16. So I've got 49, 24, 24, 16, 16. So let's add that up. 49 plus 24 plus 24 plus 16 plus 16. That is my n. That's the total number of solutions. And that number is 129. And what they wanted me to figure out was n squared, which would be 16641, and then divide this by 100 and see what the remainder is. Well, the remainder obviously is going to be a 41. And that's the answer. So number 25, 41 would be D.